In Chapter 5, we learned some of the basics of probability. We learned the addition rule, the multiplication rule, independence, and disjoint. Right? But we didn't branch too much further into probability, and that's because, honestly, you could spend months, years even, figuring out probabilities. I mean, it really is its own field of mathematics. We use a little bits of it to do some statistical lifting for us, but so we in chapter 5 we learned some of the basics, and now in chapter 6 and 7 we're going to apply those basics to two different ideas. So chapter 6 we're going to use them on discrete probability distributions, and chapter 7 it's going to be continuous. All right, we'll talk more about that in a second. But let's think back to the NBA problem we had in, I believe it was section 5.3. So you have the average free throw percentage for NBA players is 77% overall. So that's the chances they're going to make a free throw. You're going to select 3 random NBA players and have each of them shoot a free throw. So recall, this is the tree diagram. So we were like 3 players, we make a diagram, there it is. So we spent some time and made a diagram, and then we were like, okay, I've got all those outcomes, so I'm going to go write them up over here. Then I got to go find the probabilities for each one of them. Ugh. I mean, it was a lot of work. I mean, a few minutes out of your life that you're never going to get back, and that was only for 3 players. What if it had been like 30 players? Seriously, I mean, it would just be huge. I mean, actually, it would be really astronomically huge, because it'd be 2 times 2 times 2 times 2, 30 times, which is a really big number. What about 300 players? Ugh, right? There's got to be a better way. Not to sound like, an infomercial, but there really has to be. And the answer is there is. There's a formula that will find some of these probabilities for us. Matter of fact, all the probabilities for us. It's called the binomial formula. Now, we'll learn about that in section 6.2. But for right now in 6.1, we've got to lay some groundwork for how discrete probability distributions work. All right, so before we even get into that, though, let's take a moment and remind ourselves from chapter 1 the difference between discrete and continuous. Now, a random variable is going to be anything that we don't know that can happen by chance, right? So any measure of an outcome that's determined by chance, likelihood. Usually we use capital letters such as capital X for this. Now, a discrete random variable is going to have a finite or countable number of values. In other words, you can have, and if you can see down here on the graph, you can have the dots, but you can't have the inner spaces in between. It's not possible, for example, to get 2.36 of a basket. You either get 2 baskets or you get 3 baskets. You can't get the middle, right? Continuous variables, you can get into that middle, right? Over here on the right, you can get those values, like the height of the NBA player. You can get a guy that's, 7 feet 2 inches tall, but you could also get one that's 7 feet 2.3456 inches tall if you just had a fine-tuned enough measuring stick, right? All right, so that's the difference between discrete and continuous. Now, why does that matter to us? Well, you've got 2 different types of random variables, so you're going to have 2 different types of probability distributions. Chapter 6, we're going to work with discrete. In chapter 7, we're going to work with continuous. And then, I'll be honest with you, we kind of work with continuous from then on. So chapters 8, 9, 10, 11, they're all continuous, all of them. We basically trick our data sets into turning into continuous. Even if they were discrete, we'll talk about how that works later on. All right, so we're going to determine whether the following variables are discrete or continuous. So I already wrote them up. Let's see if you understand. The distance, that's something you measure from the floor to the rim on a standard NBA court. That's continuous, right? Because you could get it to be, 12.2346 feet. Right? It's not that high. All right, the number of successful shots in 3 free throw attempts. So if you go up to the line and you shoot 3 times, you're either going to make 1 basket or you're going to make 2, but you can't make 1.22, right? That's not how it works. All right, what about the height? It's like I planned this. I didn't even look down, but the height of the NBA players is continuous, right? You can get more decimal places if you just had a fine-tuned enough measuring stick, right? Whereas the number of points they score better be discrete, right? Otherwise, somebody's doing something funny with the math, right? You got to have, 100 points or 101 points. You can't have 100.23 points, okay? All right, let's go on to how do we identify probability distribution. So the probability distribution of a discrete random variable x provides the possible values of a random variable and their corresponding probabilities. You can do it in a table, you can do it in a graph, or you can do a mathematical formula. So right now we're going to look at tables and graphs. That formula bit's coming in the next section, 6.2. So here in the NBA Finals is the best of 7 series. The following table shows the number of games that have been played in every finals, dating back to 1946. Now, a best of 7 series means you have to get to 4 games in order to win the series, because once you get to 4, then the other guy can't possibly match you, right? So if the finals took 4, that means the other team scored 0. This is called a sweep, right? So it was 4 games to 0 games, right? If it was 5, that means the winning team got 4 and the losing team got 1 game, right? If it was 6, that means the winning team got 4 and the losing team got 2. And if it's 7, then, it was 3 and 3 up to that last game, and then the 7th game, the one team won. So it was 4 to 3. So it's the first team to 4 is another way to say it. So best of 7. 4 is greater than half in 7, right? So take 7 divided by 2, you get 3.5. So 4 is the next number up. So that's how many games you got to get to. All right, so our job, we have these games right here on the count. We have to find the probabilities. We are going to grab Excel and make it do it for us. All right, let's see here. And of course, if you didn't have Excel, you could still do this. This is going to be a pretty simple calculation, but let's see. We want to find the sum here. We want to know how many games there were total. 66, which makes sense because, whoops, I'm making this in 2012. And I got this data in 2012, and it started in 46. 46 plus 66 makes 2012, 1946. All right, so to find the probability, what I want to know how common 8 was divided by that total. I'm going to give that total dollar signs, the F4 button, press enter, and then I drag it down, and there we go. There's our probabilities. Oh, I better label this. This was 6.1, example 2, I think. Yep, example 2. All right, there we go. Oh, and I better save it. File, save as. I'll put it on my desktop for right now. This is chapter 6, technology, Alana, or whatever. Put your name in it or don't. It doesn't really matter. All right. I think I usually prefer it with your name in it, but I forgot where I was. There we are. Can only have one thing open at a time. All right, so I want to put these probabilities right here in the video. There we go. Oh, no. There they are. Now that should look familiar to you. You've done this before. You did it in chapter 2, right? Because these are the same as relative frequencies. When you were finding relative frequencies in chapter 2, you were also, in a way, finding probabilities, right? I mean, relative frequency is really talking about the past, what's existed. And then the probability is saying, hey, if it continues to work like this in the future, these should be the probabilities. It's like an empirical probability. All right, now don't forget the rules for a discrete probability distribution. These should look very familiar to you. We learned these in chapter 5. The sum of the probabilities has got to be 1. That's what that little symbol right there means, capital sigma, the sum. And then every probability has to be between 0 and 1. Right? No negatives allowed, no probabilities bigger than 1. So are the following probability distributions? Why or why not? So yes, this one is. They add up to 1, and there's no negative probabilities there. Right? I can say sum of probs is 1. Okay? Same thing with the other one, this one right here. It's not a very pretty probability distribution because everything's impossible except for 4, but, hey, it doesn't matter. They're still between 0 and 1 inclusive, see the or equal to, so they can be 0 and 1s, that's fine, and they add up to 1. Now down here, for this one, a big fat no. See this right here? That's a problem. We have a negative probability. I think this doesn't even add up to 1 either, which is another problem. But aside from the fact that it doesn't add up to 1, you've got the problem that you don't even have a positive probability. You have a negative probability, which is impossible. So that's bad. And I also didn't spell probability right. There we go. Now over here, some of these probabilities is not 1, it's 1.2. which is no good for us. Probabilities have to sum to 1. So that one's a no. All right, now let's look at a histogram. So I said back here, hey, you can show your distribution in a table. That's what we just did here. Or you can see it in a graph, which is right down here. There's the graph. See? Now, how did I get that? Well, let's practice. Let's remind ourselves how we do this. You go here, you highlight these. Yes, do this. Insert column. There we go. That's pretty much it. All you got to do is delete this, and then these are no good for us. Those labels, it's just labels in 1, 2, 3, 4. So if you click down here and select data, edit your horizontal or axis label, and then you want to put it in the numbers 4, 5, 6, 7 right there. So for me, it's cells A2 through A5. Okay. Okay, and then also we don't want gaps. So I'm going to I just clicked on any one of the bars. Right click on the bars, format data series, and right here where it says gap width, shrink that to 0. Close. I'm also not particularly fond of these colors. I like the ones down here. This little section right here that has like, yeah, see how it's going to make them have bars around it so you can kind of see it a little bit better. So that's just me. I like those ones. Swing, moving it over. Oh, better label it. Oh, that would be not. All right, hold on 1 second. Let me throw my label in. Let's see. Oops. There we go. All right, probability histogram. And if you're an online student, of course, you are following along and doing this graph, right? I figured I should be a little bit more, right? And then I guess if I wanted to add a label down here, layout, axis title, horizontal axis is the number of games, enter, and then axis title on the vertical, rotated, this is the probability that we were finding over here, aka the relative frequency. I don't think I spelled that right. There we go. Probability. Yep, that's right. So, ta-da, we've got that. I'll just move it over here so we can see things. All right, so that's where I came up with that in the notes for you. But you also should know how to do it yourself in Excel and should do it if you're an online student. All right, so what does the area of the 4 bars add up to? Well, it's got to be 1, right? These are probabilities. Probabilities have to sum to 1. Cool. Now, what's the shape of this distribution? It's got a little tail thing going on over here. So it's a little bit skewed left. Not by much, but a little bit. All right, we're done with this section. I will see you back here for the mean and standard deviation of this distribution.